Hello everyone, today I will present our paper, Chronus, a novel deadline-aware scheduler for deep learning training jobs. It is a joint work among Gao Wei, myself, Ye Zhisheng, Sun Peng, my supervisor Wang Yonggang, and co-supervisor Zhang Tianwei. Background and challenges. A common scheduler in modern GPU data center is as follows. Users submit application request. For example, user requires X GPU resources for this job, and the scheduler receives this request. Meanwhile, scheduler needs to monitor hardware resource state and make scheduling decision towards specific scheduling objective. GPU cluster for deep learning training. In the deep learning training jobs matter a lot. About 1,000 DL training jobs per cluster and per day in SenseTime and Microsoft based on our observation. DL training jobs require intensive resource. For example, distributed DL training jobs train with multiple GPUs, even up to thousands of GPUs. GPU cluster characteristic for deep learning training changes a lot. Thousands of GPUs exist in modern GPU cluster. GPU cluster scale is still increasing. And we conduct user survey and find that service level objective requirement in DL training. SL jobs and the best effort jobs coexist in modern GPU clusters. For SL scenario, including production development, artificial intelligence conference, and for best effort job scenario, research explorer jobs. And we also find that users can tolerate SL violations of deep learning training jobs to a certain extent. About 22% participants can accept 20 deadline delay. If we want to design a scheduler to support SL enforcement of DL training jobs, what challenges do we need to address? First, job runtime estimation. In the context of deep learning scheduler, online profiling is widely used technique. However, it requires GPU resource reservation, which provision extra resource which can be allocated for job execution. Second, how do we select a job for a mixture of SIO and best effort jobs? Based on our observation, managing and enforce the deadlines for certain jobs is necessary. However, it is also challenging. Third, the runtime speed of distributed deep learning training jobs is placement sensitive. If we do not consider resource topology, SIO job still misses its deadline when the placement is not consolidated. Existing solutions and corresponding gaps. We make taxonomy to classify existing schedulers into two dimensions. Horizontal dimension is whether it is DL scheduler. Vertical dimension is whether it is deadline-aware scheduler. We find that fewer works focus on the joint area between deadline-aware scheduler and DL scheduler. Disadvantages of existing DL schedulers. Most existing DL schedulers lack explicit support for SL requirements, mainly designed for job performance like JCT, mixed-span, or fairness across users or jobs. And to our best knowledge, Hyperschedule and Genie are existing DL schedulers considering SIO, but both of them are ineffective for realistic scenario because they do not consider the mixture of SIO and best effort jobs. Hyperschedule focuses on HPU jobs. Genie requires modification of the underlying DL framework. Current deadline-aware schedulers to support big data is not tailored for DL training jobs and is ineffective to manage DL training jobs. We list three unique features that DL training jobs exhibit. First, DL training jobs exhibit very high intra-job predictability. Second, DL training jobs naturally support the preemptive scheduling with acceptable overhead compared to the execution time. Third, DL training jobs are sensitive to placement policy. Proposed solution. Here is our system workflow, including three key stages. Job enters first stage provider to collect necessary information. Then, selector will decide which jobs to run. Finally, allocator will decide where each job runs. I will elaborate the three key stages one by one. The first key stage, provider. The objective is to fill the short-term jobs and collect job speed information, as well as minimize resource reservation for profiling. Our method includes two techniques. First, submission control. It is to restrict the maximum number of resources requested by each user. Second, dynamic capacity scaling. It is to use history trees to predict the reserved resource capacity for profiling. The second key stage, job selector. The objective is to select which jobs to run, decide how long jobs run, and judge if one SIO job can be completed within soft deadlines. Our method includes 3 techniques: admission control, list-based training, convert SIO scheduling problem into MILP. We need to specify the reward function for different types of jobs to schedule. X-axis represents the completing time of deep learning training jobs. Y-axis represents corresponding reward value. The plot shows the relationship between the completing time and the reward value. Best effort job is always constant reward value, smaller than SIO jobs. The reward value of SIO job will drop at certain points. Compared to straight SIO jobs, the reward value of soft SIO job drops gradually. It is possible that some users specify unreasonable deadline requirements for their jobs, such that the cluster can never satisfy them. We propose admission control to identify such SIO jobs. This step is triggered after the profiling phase. It is to check whether there are any solutions to meet SIO requirements of the newly submitted SIO jobs. If not, the SIO job is labeled as unguaranteed SIO job. The SIO requirements of guaranteed SIO jobs is highly ensured. Unguaranteed SIO jobs are treated in a best effort manner. DL training jobs naturally support preemptive scheduling. Hence, we propose list-based training. We divide each DL training job into multiple time periods with the same list length. We set the list length as 20 minutes for SIO list and 5 minutes for best effort list empirically. This implies our scheduling interval is at least 5 minutes. Now, list-based training enables us to model guaranteed SIO job selection task as MLP problem. The basic idea is to set cluster capacity as a resource constraint, deadline requirements as time constraint, set several variables to indicate whether job selects certain lists. Maximize reward value is our objective. Specifically, we show our formulation here. Binary variable SKI indicates whether S job selects case list. Binary variable SPI indicates whether S job satisfies case deadline. VPI is reward value. Equation 3 limits resource provision size. Equation 4 guarantees SIO job can be finished before soft deadlines. Equation 5 guaranteeing SIO job is assigned with one feasible solution. The feasibility of MLP optimization problem implies deadline guaranteeing. This formulation is also adopted in admission control technique, which is mentioned before. The third key stage, resource allocator. The objective is to decide where jobs run and mitigate potential deadline violation brought by consolidation hostile jobs. We have 2 techniques. The first one is to apply run-up technique on jobs with SIO lists. Second one is to apply local surge placement strategy on jobs with best effort lists. You can see more details about local surge placement strategy in paper. Run-up technique for guaranteed SIO jobs. We need to define the consolidation-friendly jobs and the consolidation hostile jobs in paper. And the run-up technique involves this definition, which is delivered in paper. The approach is to run up the number of requested GPU of guaranteed SIO job to 1, 2, 4, 8n. This technique can ensure the existence of a consolidation solution for guaranteed SIO jobs. And now, based on this observation, we can change the resource constraint 3 to constraint 6 for MLP optimization. And experimental results. Testbed for experimental setup. We have 2 homogeneous GPU clusters. Each GPU node contains 8 GPUs. The summary of workloads in our experiments is here. And the header trace is from SenseTime and failure trace is from Microsoft. In different workload varies in trace source, proportion of SIO job and best effort job, cluster size, the number of job. More trace information can be seen in our paper. Our evaluation metrics. The weighted deadline miss rate for SIO jobs, and job completion time for best effort jobs. And we have 6 evaluation baselines. General scheduler, deadline aware scheduler includes EDF, on early deadline first, Journey, 3 sigma, and deep learning scheduler includes SEMIS, TESIS. End-to-end evaluation macro benchmark. Deadline-aware schedulers perform better than DL schedulers. Chronus can guarantee SL deadline and maintain the efficiency of best effort jobs. Especially, Chronus leverages solver deadlines to significantly decrease the weighted deadline miss rate. More breakdown experimental results and Kubernetes results can be seen in our paper. Conclusion. When making innovations in the designs of job profiling, selection, resource allocation to improve the scheduling efficiency and effectiveness. Extensive simulations indicate that Chronus outperforms 6 state-of-the-art scheduling algorithms in reducing the deadline miss rate and job completion time. Thank you.